This lesson is probably one of the most important lessons of this unit, and we're going to learn how to solve first order linear differential equations. And so we've talked about what makes an equation linear in the very first lesson, and there were two requirements. One was that the dependent variable and derivatives of that dependent variable all have to be to the first power. And second was that the coefficients throughout the equation all have to be functions of the independent variable. And so this is what your typical first order linear differential equation will look like. So we need to learn how to solve this. And similar to the things we've done throughout this semester, we will use what we've already learned to figure out how to solve this one. So one of the key parts to the solving process is to put our equation in standard form. And standard form essentially is to get the leading coefficient here to be a 1. And so what I would have to do is I would have to divide this equation here by a1 all the way through. And so if I divide the whole thing by a1 all the way through, this becomes 1, because a1 divided by a1. This here would become a sub 0 divided by a sub 1, and we're going to call that p of x. So again, p of x is equal to a sub 0 of x over a sub 1 of x. And then this here would be g of x over a sub 1, and we're going to call that f of x just to make it look nicer. So again, g of x over a sub 1 of x. Right, we changed the name to p of x and f of x because if this is a function of x over a function of x, it's just one giant function of x, and makes it much simpler just to call it p of x, and the same thing here for f of x. So this is standard form. The leading coefficient here in front of the dy dx is a 1. Right, that's key. Got to remember that. Standard form. And we're looking for a solution to this differential equation on some interval I, for which both the coefficients p of x and f of x are continuous. And why is that important? Well, you know, they have to exist, which x's would make them exist, but also they're rational functions. I mean, look at this. A sub 0 over a sub 1, g over a sub 1. Essentially, a sub 1 can equal 0. And if a sub 1 equaled 0, if you think about this original equation here, if a sub 1 equaled 0, then it would wipe out this whole first term. There would be no derivative in the first place, and therefore no differential equation. So this all kind of goes hand in hand. This section is really important because it's going to be the basis for a lot of what we're going to do the rest of the semester. This is first order linear differential equations. We've solved first order equations a bunch of different ways so far this semester. And the idea being that we've used kind of what we've learned before to learn the next method of solving. Well, what's going to happen is after this first unit, we're going to learn about higher order differential equations. Equations that have second derivatives, third derivatives, fourth derivatives. But all of them are going to be linear. Okay, that's the one thing that's going to tie them all together. They're not going to be separable or exact or homogeneous. They're all going to be linear. And so what we do with the first order linears is really going to propel us into what we do with the second, third, fourth order linears. Okay. So when we talked about exact differential equations in the previous lesson, we talked about the concept of an integrating factor. And the idea was we tried to use an integrating factor to take something that wasn't exact and make it an exact differential. And if we could find that function, and we're going to call that mu, if we could find that function mu for which this would happen, we could, again, take something that's not an exact equation and make it that. So we're going to use that tactic here for linear. First thing I'm going to do is I'm going to rewrite my linear equation in this form. Essentially, it's that standard form that we just looked at, but breaking apart the dy into dx and moving the f of x over to the other side so that now the equation is equal to 0. So this is still the same linear equation I just showed you, only that it is, rewritten in this format. The p of x and f of x are the same p and f of x that we had previously. All right, so then what we're going to say is let's try and find this mu such that when I multiply it through this equation, I now get an exact differential equation. So that means the mu here gets multiplied by the dy, the mu gets multiplied by this p of x y minus f of x dx, and then if it's also multiplied on the other side, it's multiplied by 0, which still stays 0. Okay. So if this is an exact differential equation, then this coefficient in front of the dy would be what we were calling n, and all this in front of the dx would be that function that we called m. And what we learned was that m with respect to y had to equal n with respect to x. Those partial derivatives had to equal each other for the equation to be exact. And ultimately what we're looking for is what mu would make this happen. Okay? Well, if we take the partial derivative of n with respect to x, okay, that would be the partial derivative of mu with respect to x, so that's here. And then if we did the partial of m with respect to y, that would be the partial with respect to y of all this. This was my m. So again, here's n, here's m. Okay. Now, if you're doing the partial derivative of a function of x with respect to x, that's the same thing as doing just a standard single variable derivative. You know, it's the derivative of a function of x with respect to x. There's no other variables here, and so this would be just the derivative of mu with respect to x. So that's just a standard derivative there on the left-hand side. Now, if we look at the right-hand side, and we want to take the derivative of this whole thing with respect to y, okay? Well, there's something missing here. There should be a y right here, because that's the y here, the y here. So that just should be right there. So if we take the derivative of this with respect to y, okay, x is treated like a constant. So this x would be treated like a constant, this p of x would be treated like a constant, and this f of x would be treated like a constant. Well, first off, this one would be a constant multiple. So we're going to pull that out. So there's the mu, it's going to be pulled out. Then we're going to take the derivative of the rest of this here with respect to y. Well, this is p of x times y. So that would just give me p of x. And then this is f of x. Well, this is just a constant essentially sitting by itself because x is treated like a constant. So then that one right there would be 0. So that one's gone. So what we get? We get mu of x, which we pulled out, times p of x. So that we get it there. And so these have to be equal to each other, right? These are the derivatives of n with respect to x and m with respect to y. So they have to equal each other. If we look a little bit closer at this, we find out that actually this is separable. If I move the dx to the right-hand side and the mu I divide over to the left-hand side, I end up with this equation. Ultimately, what are we doing here, right? Don't lose sight of what we're trying to accomplish. We're trying to find the factor mu that makes this an exact differential equation. So we're trying to solve for mu somehow. So now that we're here, the next thing we're going to do is we're going to integrate both sides of this equation. In which case, if we integrate both sides of the equation, this is d mu over mu. That's your standard logarithm integral. So the log of mu. On this side, we have the integral of p of x dx without knowing exactly what p of x is, other than we said it was a sub 0 over a sub 1. That's all we know, but we don't know what either of those functions are. The best we can say is that this is the integral of p of x. And then what we can do is we can get rid of this log and just have what mu equals by exponentiating both sides. So e to the log, they cancel, then e to the integral gives us that mu should equal e to the integral of p of x dx. So there is your integrating factor, okay? Mu should be e to the integral of p of x dx. And p of x comes all the way from the original differential equation put in standard form as dy dx plus p of xy equals f of x. So the p of x we're talking about is this p of x right here in front of the y, when we put the original differential equation in standard form. So that is where we are right now. So now what we're going to do is we're going to take that integrating factor and we're going to multiply it through the differential equation. We're not going to worry about a constant of integration to come out of the previous step, because we're going to throw the constant of integration in later. It's going to work itself out. We could put it in now, but we're just kind of writing more than really is necessary. We're going to fill it in later. So we take the original differential equation in standard form, okay? Remember, which was dy dx plus p of xy equals f of x. What we do is we take this dx and we multiply it through so that it's going to be dx here and dx here. And so that's what you see. So you see dy plus p of xy dx f of x. And then we have that integrating factor multiplied through the whole way. Okay? Now here's the key to why this works. Once we multiply through by that integrating factor, this is an exact differential, which means this side of the equation is the derivative of a given function. And the function that it's the derivative of is that function right there. So we could write this whole side out as what it really is. It's the derivative of this. Now take a quick look at that. If I were to take the derivative of e to the integral of p of x dx y, this is a product, and I would use the product rule. I would take the derivative of y, which would give me e to the integral of p of x dx times y, times dy, derivative of y, plus, then I'd have to do the derivative of this, exponential. Well, how do you do the derivative of exponential? You rewrite the exponential, you multiply by the derivative of the exponent. Well, that would be the derivative of the integral, which would just give me p of x dx. And then we have y itself. We would still need the original second function here. And so this would be the product rule for this derivative. Well, that's exactly what you're looking at right here. So noticing that, okay, and that's really the key here, is noticing that this here is the derivative of this function is kind of the key for how this works. The right-hand side is still just the integrating factor times what was already there. And so what we're trying to ultimately do is solve the equation, right? We want to know what y equals, right? What function satisfies the differential equation? Well, now we're at this stage here. If we could get rid of this derivative and then get rid of this exponential, we could figure out what y equals. Well, how do we do that? Pretty simple. One, we get rid of the derivative by integrating. Well, we'd have to do that on both sides. So we integrate the derivative. They cancel each other out. So then we have the integral here of e to the integral of p of x dx times f of x dx, whatever that would be, then plus c. Here's where the c is now coming into play, because you would integrate this. Whatever that ends up giving you would be some function plus c. Then what we would have to do is divide this over to the other side, and we could figure out what y equals. Well, if you divide by e to the integral of p of x dx, that's the same thing as multiplying by e to the negative integral of p of x dx. Just change the exponent, essentially bring this up to the numerator. And so what we end up in the end is that y equals e to the negative integral of p of x dx times the integral of e to the integral of p of x dx times f of x dx plus c times e to the negative integral of p of x dx. The idea is both of these pieces here, that's something I think a lot of people mess up that you need to be aware of, is that both of these pieces here across the addition are divided by this, or in this case multiplied by e to the negative integral of p of x dx. All right, so what are we looking at? Well, what we're looking at is the solution to the linear differential equation. We could treat this like it's a formula, and we could just pick p of x out from the original differential equation. We could pick f of x out from the original differential equation, plug them in, integrate everything that's sitting in front of us. Boom, we have our answer. I don't particularly care for that all that much. We're going to follow more of the process of how we made our way through here. I'm going to shortcut certain steps because you're going to see a pattern repeating itself over and over and over and over again. But we're going to get through it. It seems like a lot, but when we put actual functions in for p and f and etc., it's not as bad as it looks. In fact, you're going to find that linear first order differential equations become one of the easiest ones for you to solve when we're going through the process. But anyway, here is our solution. This shows us that there is a solution to a first order linear if we follow this process, and that's what it would look like. So as far as our steps to solving a first order linear equation, first thing we want to always make sure you do is put your equation in standard form. That is going to be key. If you miss that step, everything you do will be wrong from there on. Because what we need to do is we need to identify what p of x is. Why? So that we can create our integrating factor. Integrating factor is this mu, which is e to the integral of p of x dx. Once we do that, then we'll multiply our standard form equation by that integrating factor, realizing that the left-hand side is automatically the derivative of the integrating factor times y. Okay? That's what's always going to happen here. I have a bracket in the wrong place. This bracket should be here, not here. Okay? That's always what's going to happen on the left-hand side. The right-hand side, however, will always be our integrating factor times f of x. Again, f of x coming from when it was already input in standard form. Integrate both sides, solve for y, you're done. Okay? So it's a fairly simple process. So here's an example. This is probably one of the easiest examples you're ever going to come across. And so dy dx minus 3y equals 0. Notice that this is linear for all the reasons that we've talked about before. Dy dx, y, first power, this is a 1, a minus 3, and a 0. They're all functions of x. They're all constants, but they all could be functions of x. First thing, put it in standard form. It already is. It is already, and p of x is negative 3. So then your integrating factor, mu of x, is e to the integral of negative 3 dx, which will equal e to the negative 3x. Next we're going to do is multiply this equation, the original equation, through by that. So I'm going to get e to the negative 3x times dy minus 3e to the negative 3x times y dx equals 0 times e to the negative 3x dx. Well, 0 times anything is 0, so that's still just a big 0 over there. This, you have to realize, is the derivative of e to the negative 3x times y. And again, double check that. If I was to do the derivative of this, I would need the product rule, in which case I take the derivative of y, which would be the dy, times e to the negative 3x, plus the derivative of e to the negative 3x, which is negative 3e to the negative 3x, times y. And so you see, you get exactly this. So we can always rewrite this left-hand side as the integrating factor times y, and the derivative of that. Okay? And this side is still just 0 on the right. So now what I'm going to do is I'm going to integrate both sides. So these cancel. So I get e to the negative 3x times y equals the integral of 0 would just be c. With respect to x, it would be c. With respect to any variable, it would be c, but with respect to x. Solve for y, you move the e to the 3x over, and we get y equals c e to the positive 3x. Why? Because I could divide by e to the negative 3x on both sides, but dividing by e to the negative 3x is the same thing as multiplying by e to the positive 3x. And so there's your solution. All right, let's get rid of all that. And that's it. Pretty simple. It's not much to this. The integration is pretty simple. I mean, obviously it's going to get a little bit more involved than this one was, but there's your solution. Now, something to take note of. Well, two things. One, this original equation was equal to 0. Okay, so we have the f of x in this case is 0. All right, and the solution to this differential equation looked like this, in that it was just built off of y equals c times some function. Okay, that's the pattern you see for this. Oh, I couldn't say a pattern, it's the first example. But what you see in this example is that this one was equal to 0, so f of x is 0, and the solution was y equals c times some function. Okay, let's just say, I don't know, some solution function. So let's say f of x. Okay, just keep that in mind. That really doesn't do anything for you right now. Okay, that will play a role in the next unit when we talk about building solutions to larger linear differential equations. Okay, so just bear in mind there. Okay, second thing, again, doesn't really give you anything right now, but will later, is that this equation has constants as all the coefficients. Everything's a constant. Okay, 1, negative 3, 0, all the functions of x that are in this thing are constants. And the solution to the differential equation happened to be an exponential function. Again, doesn't mean anything to you right now, but in the next unit, we'll wrap around back to that thing. All right, let's do another example. And keep in mind what I just said of those two things. You'll see that pattern continue through all the examples we do. If it's equal to 0, and if there's constant coefficients, two things could happen. One, if it's equal to 0, you just get this one piece that has a c attached to it. And two, if it has all coefficients that are constants, it has an exponential solution. So here's another one. This is definitely linear. It's not in standard form, but it has everything a linear needs. As the dy dx and the y are first power, and all the other coefficients are all functions of x. Now notice these are not constants all across the board, and it's not equal to 0. So all the things I said in the last example are not happening here. And let's compare the answer we get here with the answer we got in the previous one. That'll give you a little bit more of what you're going to need in the next unit. The first thing I have to do, though, is put this in standard form. I got to divide this x through this equation all the way through. So what we get is dy dx minus 4 over x y equals x to the 5th e to the x. And so we do that because we want to identify p of x. And so p of x is that negative 4 over x. And so my integrating factor is e to the integral of negative 4 over x dx, which will be e to the negative 4 ln of x, because it's 1 over x dx if I pull out the negative 4. Now we want to simplify this, but be careful. I see people mess this up a lot. Let's bring the negative 4 in first as a power, and then we can cancel the e in the log. You cannot cancel this e in this log using the inverse property without bringing the 4 in first. And so what we end up with is e to the log of x to the negative 4, then cancel, we get x to the negative 4. Okay, so there's our integrating factor. So then if we multiply that through the standard form equation, I'm going to get x to the negative 4 dy minus 4 over x times x to the negative 4 y dx equals x to the negative 4 times x to the 5th e to the x. And again, what happens is this side of the equation, if you look really close at it, is the derivative of x to the negative 4 times y. It's the integrating factor times y. And again, if I just check it, and now this is the last time I'm going to do this, because if we see this pattern developing every single time, what we're going to do from here on out is we're going to skip to this step. We're going to start here once we find our integrating factor. But anyway, derivative of y would be the first piece times x to the negative 4 plus the derivative of x to the negative 4 times y. Well, derivative of x to the negative 4 is negative 4 x to the negative 5. Well, that's exactly what this is. Negative 4 x to the negative 5, because this would come up. This x to the negative 1 would come up and give me x to the negative 5 times y, right? Y would stay the same. And so you see that product rule working out just as well in that one. Right? The right-hand side, well, if I have x to the negative 4 times x to the positive 5, I get just x e to the x out of that. And so now it's time to get y by itself. So what am I going to do? I'm going to integrate both sides of this. Integrating the left-hand side just gives me x to the negative 4 times y. Integrating the right-hand side, I need to do that by parts. That's a by parts integral. And so if I did that by parts, I would come up with u equals x, dv equals e to the x, du equals dx, and v equals e to the x again. And so I would come up with the x e to the x, which would be u times v, minus the integral of v du would give me e to the x dx, which would give me e to the x again, throw plus c on the end, and there we are. So now what we have to do is we have to get rid of this x to the negative 4, and we would come up with the fact that y equals multiply x to the positive 4 all the way through, so that would be x to the 5th now, e to the x, minus x to the 4th, e to the x, plus x to the 4th times c. Really not a bad one again when we solve this thing. Here's your solution to your linear differential equation. Notice this solution is much larger than the previous one. And that has a lot to do with the fact that this wasn't equal to 0. So this one wasn't equal to 0. The f of x itself, even after we put it in standard form, was x to the 5th e to the x. And we got really two parts to our answer. There's this piece right here that doesn't have any c's attached to it. Okay? And then there's this other piece that does have a c attached to it. Again, that means nothing to you right now, but we do have these two parts here. One that does have a c attached to it, I'm going to call that y sub p, or y sub c, and this other piece that doesn't have a c attached to it, which I'm going to call y sub p. Why am I calling those things? Because it's going to mean something later, but right now you just know them as the part with the c and the part without the c. And that was because we had this not equal to 0. We didn't get this last time. Last time, when it was equal to 0, this is all we ended up with in our answer, the piece that did have a c attached to it. Again, this means nothing to you right now. We just need to get to this point. But the more I kind of point these things out now, it'll help you later. All right, here's another one. Again, everything you need for linear. It's not in standard form, but it is linear. And notice the 0. So I'll put it in standard form first. So that'll be dy dx plus x over x squared minus 9 y equals 0. So here's my p of x. So my integrating factor, mu of x, should be e to the integral of x over x squared minus 9 dx. Well, in order to do that integral, you would need substitution. So I'm going to say u equals x squared minus 9. Du would be 2x dx. We don't have the 2, so divide. So this would just be du over u here with an extra 1/2. So in the end, I'm going to get e to the 1/2 log of u being x squared minus 9. Just like before, I want to get the e to the log to cancel, so I'm going to have to bring the 1/2 in first, and then I can cancel, in the end giving me x squared minus 9 to the 1/2. So that's my integrating factor. So then what I'm going to do is I'm going to say if I multiply this original equation, the standard form original equation, by that integrating factor, I know that the left-hand side is going to turn into the derivative of that integrating factor times y. And the right-hand side is going to be this times the integrating factor, so still just 0. Then I'm going to go ahead and integrate both sides of this, canceling, giving me x squared minus 9 to the 1/2 times y, and here I'm getting c. I'll divide this over, and I get that y equals c over x squared minus 9 to the 1/2. Again, taking note that I got one part to my answer that has a c attached to it, and it was one of those equal to 0 ones. So just keep note of that. But there's our solution. Really wasn't that difficult. I mean, this was really the only integration you had to do, and that was basic substitution, giving me a log integral, so it wasn't that bad. Again, that one, just for your quick reference, would have been 1/2 du over u when we did the substitution, and that would have been a log integral. We bring the 1/2 in to get rid of the e in the log. So that's a step that a lot of people mess up. If you don't cancel that e in that log, then this is going to be wrong, and we're going to get thrown off throughout. Here's another one. This one also has an initial value problem attached to it. We ignore that for now. We'll do the solution to the equation first. This one is not equal to 0. It is in standard form. P of x is 2x, so my mu, if my computer will work again, and my mu is e to the integral of 2x dx, which gives me e to the x squared. And so if I multiply this equation through, I know that the left side turns into the derivative of e to the x squared times y. The right side turns into f of x times the integrating factor. I'll integrate both sides, canceling this out, giving me e to the x squared y. And then the integral here, how are we going to do this integral dx? Well, the way we're going to do this integral is by substitution. U equals x squared, du equals 2x dx. I don't have an extra 2, so I'll divide. So I'm going to get 1/2 integral of e to the u du, because x dx is going to be my du over 2. And so this will just be e to the u is the integral of e to the u, so I'm going to get 1/2 e to the u was x squared, plus c. Don't forget that plus c there. Okay. And then what's going to happen is I'm going to divide this over to the other side, and I would figure out that y equals 1/2. The e to the x squareds cancel, plus c times e to the negative x squared. I do that so I don't have to write it as a fraction, c over e to the x squared. I just make the exponent positive and bring it up. So there's the solution to the differential equation. Again, pretty easy. I'm going to beat this down as much as possible, but notice it wasn't equal to 0, and we have two parts to our answer. One piece that doesn't have a c attached to it, and another piece that does. Okay? All right. All that aside, we now have the initial value problem to solve. This is the solution to the differential equation. The solution to the initial value problem is what c would have to be to satisfy this condition. So in this case, x is 0, y is -3. So you get -3 equals 1/2 plus c e to the 0. Well, e to the 0 is 1. So if I just subtract 1/2 from 3, 3 was what? 6/2 minus another 1/2 would be what? -7/2 is my c. So then y equals 1/2 minus 7/2 e to the negative x squared. That solves the IVP. And we're just going to keep rolling. Here's another one. Not in standard form, so we're going to do that first. Yeah, there's also an initial value problem attached to it. And so we're going to get dy dx plus 1 over xy equals 2 is our standard form because we have to divide everything through by x. All right. P of x, pretty clear, 1 over x. So our mu is e to the integral of 1 over x dx, which would be e to the log x. E and the log cancel, so just x. So then that would tell me that the left-hand side will turn into the derivative of x times y, and the right-hand side is 2 times x. Integrate both sides, we get x times y equals the integral of 2x would be x squared plus c. Divide by the x, you get y equals x plus c over x. Done. I mean, I told you that once you get into these linears and you realize that there's something happening every time, the same every single time, these will be one of the easiest ones you learn how to solve, which is good because we're going to base what we're going to do in the next chapter off of this. All right, so now we got the IVP here where x is 1 and y is 0. So y is 0, x is 1. We find out that essentially c has to equal negative 1. So the solution to the IVP would be that y equals x minus 1 over x. That solves the IVP. All right, so here, this one is tricky. There's a little thing we're going to do to this that's going to allow us to use linear equations, linear differential equations. This trick that we're going to use is not something you will do on every problem. In fact, this should be an absolute last resort. You've tried everything, and then you look at this, because it really rarely will happen, but because it could come up, we have to give you an example of this. So if I look at this right now, it is not linear. It is not and will not ever be in the form of dy dx plus p of xy equals f of x. Okay? There's no way I can do that. Because one, I have the y squared, right? Remember, y and dy dx, both of those have to be to the first power. So no matter what I do, I won't be able to get this in that form. So it's not linear, where y is the dependent variable and x is the independent variable. So what are we going to do? Well, what I would normally say to do is, okay, well, what else could it be? Is it homogeneous? Is it exact? Is it separable? And what happens is, it's actually none of those things. It's not homogeneous, because this right here, two different terms at different degrees. It's not exact because your partial derivatives aren't going to work out. It's not separable because I can't get the x's and the y's to split apart. And so we really have nothing here. If we had one of those other ones, I would go that way. We have nothing. So what we're going to do is this trick. The trick we're going to use here is, this is a proportion. I have a fraction equals a fraction. That's a proportion. And what happens in a proportion is if you reciprocate both sides, okay, flip them, the proportion still holds. The equality still holds. So essentially, I can write this as dx over dy, if my computer will allow me, equals x plus y squared over 1. And that really still holds in terms of its equality. But what I did in doing so, when I flip this over, I reversed the roles of x and y. Now x is the dependent variable and y is the independent variable. So the differential equation I'm looking to turn this into would be something in the form of dx over dy plus p of y times x equals f of y. And if I can turn it into something that looks like this, then I can think of this as linear in terms of x as the dependent instead of y as the dependent. Is this ideal? No. But will it help us try and find a solution? Yeah, because we don't have any other options. And so if I rearrange this now, I can write this as dx over dy minus x equals y squared. And so I get it to look like this, where p of y is -1 and f of y is y squared. And so my integrating factor is going to be mu of y, because remember we switched them around, so it's e to the integral of p of y, which would be -1 dy. So it's going to be e to the -y. Okay. Then I'm going to multiply through by that integrating factor, which is going to turn the left-hand side in the derivative of the integrating factor times x now, equals, on the right-hand side, it's going to be f of x times the integrating factor, so that's y squared times e to the -y. And then I'm going to go ahead and integrate both sides, canceling this out. It would require me to do this integral with respect to y. Well, I'm going to need integration by parts to do that, and in fact, I'm going to use the tabular method. So y squared and e to the -y are my u and my dv. So this will be 2y and then 2, then 0. This will be negative e to the -y, e to the -y, negative e to the -y. I'm just, differentiating this side, integrating this side, match them on the diagonal, plus, minus, plus. It's just a quick way to do integration by parts over and over again. So what we end up with on the right-hand side would be -y squared e to the -y, then minus 2y e to the -y, and then -2 e to the -y plus c. The right-hand side turns into e to the -y times x. In this case, we then solve for x. Instead of solving for y, we solve for x by dividing this through, which would give us -y squared minus 2y minus 2 plus c e to the positive y. Again, because if I divide by e to the -y, it's multiplying by e to the positive y. So we get a solution. Now, it's not explicit for y equals, it's explicit in terms of x equals, but it's still a solution, right? So that little trick is helpful, but rarely works. But it worked in this example. I don't look for that right away. Again, one of the last resorts. It has to be a perfect proportion for it to work. But if it does, and it gets you through, great, we're happy to get a solution. We still have this initial value part to deal with as well. Now this initial value part, we're not flipping anything. It was given in this form. That's your x, that's your y. Regardless of what we flipped around after the fact, this was given in this form, y of -2 equals 0. So there's your x and y. So if I use that in here, what I'm going to get, let's get some space in here. What I'm going to get is x is -2, y is 0, so I'm going to get 0 minus 2 plus c e to the 0 is c times 1, and so that tells me that c equals 0. Okay, so then x equals -y squared minus 2y minus 2 solves the IVP. All right, so a unique example, but an example that probably should be shown so that you can see that this is a possibility in the solving process. So there's linear first-order differential equations. Again, pretty simple to solve. We skip a couple of steps in the solving process once we get good at this to make it go even faster. And we're going to need this moving forward in the next unit to solve these higher order linear differential equations.